Come on. Yes. We're live.
Oh my
Did the bell ring?
No, not yet. We got like 1.5 minutes.
Is that coffee like mocha or something?
Huh?
Is that coffee like mocha?
I don't know.
Oh, real
This is beer.
This looks like chocolate.
That's not what smells like chocolate though. It's delicious.
Can you stop there? I don't know.
Do you have to go there?
No.
So text Emmy and tell her that we're live.
Yeah, I did.
Oh, it's glorious. We're back in business.
Oh, I have a question about what you're
It's
doing
real
up there.
good otherwise.
Yeah.
So you said that it was decreasing and increasing at 0. So is that? Is
You want to talk about that right now? Wow.
Is it over?
Yeah. We're going to talk about that.
Okay.
We're going to have an argument about it. I think I know what team you're going to be on.
Well, it is live.
Where's the bell?
This live service brought to you by Optical.com.
Are you off?
It's lunch that doesn't ring.
Huh?
So the bell doesn't ring during lunch.
Oh, yeah. Let's go.
I got it.
So we're live on YouTube now, right?
Oh my god.
Hopefully we're going to get lots of followers now.
Yep.
It's very behind.
Yeah, it is behind, which is fine.
Yeah.
I mean, I don't care about that. Okay, so do you guys have questions for me? Do you have questions for me about anything
Like homework?
homework related? Yeah.
Yeah, because we go over all the drawing the graph ones, like 216 through 218.
Yeah. Yeah. So, now I'll be honest with you, like, these drawing the graph ones, the math is really good here. And there's a lot of good stuff that you have to do. But I will be totally transparent and honest with you. The way the book packages the given information sucks. Like, they could have packaged it just in a much more, to make it easier to read. And they could have written it exactly the way they have it, just arranged it on the page differently. But it's a free book, you get what you pay for. So, for this is number 216. So they give us this information that f of x is greater than 0, and f prime of x is greater than 0. And then they give us these intervals. Now, the way they gave you the intervals is terrible. But they say that these two things are true.
What does the over mean? I don't know what that means.
Like, if they, well, let me write this down, then I'll explain it. X is greater than 1, and x is between -3 and 0. I wish they would have put this one first. Like, we think left to right. Why would you put this one first? Okay? Now, over means, and over just means, if I say that function is increasing over the interval 1 to 2.
Okay.
Like, that's what that means. Like, and you probably are maybe more used to writing it like this.
Yeah.
Okay? Which is fine too. Okay? So they tell us these two pieces of information, and then they also tell us that f prime equals 0 between, I think it's 0 and 1. Okay? So we got that information. And they're asking us to use that information, synthesize that information, and sketch a graph of this function. Okay? And they said sketch a graph of this function on the interval from -3 to 3. Okay? Now, I'm going to go ahead and stick these values on here just because it might help me sketch my graph. Because those values here are showing up over here. All right? So what you have to do is you have to now take this information and process it and say, what is this right here telling me about the function? Okay? Well, what does this mean graphically? What does it graphically mean about f if I tell you f is positive?
Oh, above zero.
It's all above zero. It's above the x-axis. Okay? What does this mean? If I tell you f prime is positive, what does that mean about f?
All above zero.
No, that means f prime is all above zero. Okay? If f prime is positive, yes, f prime is all above the x-axis, but f is always increasing. Okay? So f is increasing on these two intervals. And f is positive on these two intervals. Okay? Now what does this tell me about f? It's flat. If the first derivative is 0, the function's not changing. Right? Okay, so I got to draw something that's positive and increasing between -3 and 0. Then I got to draw something that's positive and increasing for bigger than 1. And then I've got to draw something that's flat between 0 and 1. Right? So, there you go. Did these two right here have to be the same steepness?
No.
No, there's nothing here that indicates that. Okay? Could they be different steepness? Absolutely. Did they have to be even flat, or not flat, linear? No. One of them does. Which one of those three branches has to be linear?
One more to one.
Like, you mean this one?
Yeah.
You think that one has to? Why do you think that?
I mean, if it goes forever, if it's like exponential, wouldn't it have like some kind of?
But I have no idea what the rule is. I mean, I don't know that it's exponential or anything. Could they be curvy? I mean, could I have drawn this? And would that have worked? It's got to be flat right there. Because that's the only way that you can make the derivative be 0. Okay? Yeah.
So if I remember correctly, it doesn't say that they have to be differential or couldn't you have a piecewise function as well?
You could have had a piecewise function. Actually, this is even a piecewise function, most likely.
Oh.
Okay? You mean with gaps?
Yeah.
Yeah, absolutely. Because they said you did not have to be continuous or differentiable. Okay? Which this function right here is continuous everywhere, right? But it's not differentiable right here. Ooh, I don't know if this is going to erase. And right there. What are those points called? Do you remember? Those aren't inflection points. An inflection point is where the function changes gravity, where the second derivative changes sign. Those are points where the function is continuous but not differentiable. It's where the derivative is not continuous. If you think about what the graph of the derivative function would look like, if you graph the derivative of this function right here, okay, I can just, if I graph it right here, it'd be a positive number between -3 and 0, so it'd be like this, and then it would be a same positive number, or about the same. This one might be a little bit steeper, from 1 to 3. But what's happening between 0 and 1? The derivative is 0, right? The derivative is not continuous there. What do we call that? We had a name for that. I remember teaching it to that camera right there, but there was a big glass wall here.
Discontinuity?
Nope. I mean, those are discontinuities in the derivative, for sure. But that's not the word we called it. I'm surprised you guys out of 4 groups of kids, actually, the first group, there wasn't one person that remembered what it was. No. Well, no, they didn't. This is the first live stream that worked. It's called a cuss. Does that ring a bell?
Yeah.
Okay. Now, oftentimes, when I have real kids, I tell a story about my daughter, Rachel. My daughter, Rachel, is a freshman this year, but she's going to be embarrassed when I keep telling stories about her when she's like, sitting in class. But when she was like 3 years old, 3.5, maybe 4, I don't know, she learned how to ride a bike. Okay? And she learned how to ride a bike really pretty early and just got right on the thing and took off. But she rode around the park. So the first time we went out on the street, and there's one section of our street that has a sidewalk, and it's only about 30 yards long, and maybe not even 30 yards. Okay, there's no sidewalks anywhere else on our street, so she wanted to ride on that sidewalk and the sidewalk kind of looked like this, like that, and then like that, and it literally was that. It was not smooth. Okay? So here's Rachel on her bike. Okay? I don't know how to draw a bike, but. Okay?
Uphill or curve?
She was going up. Going towards that point. She's riding along. She gets right here. Stop. Got off the bike. Why'd she do that? She didn't want to go uphill? Well, that could have been that, but I don't think that's why she did it. Because she understood what a cusp was. She understood that that point right there was a point of non-differentiability but continuous. We had a continuous path there, but it was not differentiable there. She understood that at 4 years old. Because what was she going to do if she did that? If she made that path, what was she going to do? Crash. Because it wasn't smooth. Like, this transition needed to be smooth, right? In order for her to, make that, it had to be smooth because, these wheels are, always, it's like the sidewalk is always tangent to your wheel, right? So, she got off the bike and walked it up. I said, Rachel, genius. You understand what continuous but not differentiable. How amazing is it? So it is what it is. Okay. What else? Other questions? You want to do another one like that?
Yeah.
Text Emmy and ask her if she can read this. If she's watching.
I think she is.
Emmy, are you watching? Shout out to Emmy. Emmy, hope you're feeling better. This is 218.
She said, yes, I'm watching. And she can read it.
Okay, good.
Is it like over there? Would it be backwards if you read like a word?
Oh, yeah.
What are you guys saying?
On the screen, it shows it's like inverted.
Yeah.
Yeah, but she's seeing it regular. I hope she reads it.
Yeah.
That way you could, if you were looking at it wrong, so then you could look your arm and it wouldn't screen.
That's how you guys. That's how I made my videos before.
Okay.
I wrote on a glass wall behind this camera, or on a big glass board, and I wrote normal, but I reversed the image. So if you watch those old videos I made, it looked like I was writing backwards with my left hand.
Yes.
Did you ever wonder how is he doing that? It's a trick with the camera. -3 to 1, -1, and one to 3. Yeah, somebody told me they used to watch them in 1.5 speed.
Well, I did.
Is that you? I thought I remember somebody
I
saying
watched
that.
them in 2x.
2 times. How could you even understand this?
Yeah, I don't know if I can understand
I
that.
tried 2 times and I was pausing a lot, so I went down to 1.5 and it worked better.
Every time I heard it was like normal 5 colors, but his voice sounded really slow.
Yeah, I put it back down to like 1, and then it was just like you talking normal.
But what happened when I would like make mistakes and I would be like, "Whoa, whoa, whoa," like make weird noises? Like, how did that look?
You like a couple of the tangents you went on, like I could tell were like meant to be slower, but like because I had them sped up, it was all just like one really quick tangent.
What do you mean tangent?
Like you would like go off into like a different train of thought about something that happened or that you remembered, and then you would just like it just went by like that. I was like, okay.
Yeah, but some of those are some of the best moments. Okay, so here we go. I think I wrote this down right. Again, the way they package this information is terrible, but we've got this. Second derivative is negative between negative 1 and 1. What does that mean for your function if the second derivative is negative?
Concave down.
It's concave down. Okay? Mr. Critch is teaching this right now. Literally, right now. I just walked into his room and he was talking to a student about, oh, the rate of change is decreasing. That means it's concave down. Like he's teaching that right now. Okay? What does this mean if the second derivative is positive? It's concave up. Okay? Then we got a local max at 0 and a local min at 2. And wait, no, these are both mins, I think. No, I think I. Okay?
That's what we're working function. I don't know how to do that.
Yeah, we would have discovered that pretty quickly. That was a typo. Okay, so now we're going to sketch this graph. Here we go. Negative 3, positive 3, negative 2, 1, 1, 2. Okay? Okay? So, what I would do when I was sketching this graph, what I probably would do is I would jump on this first, just to kind of give me an idea of some general shape. So because I know I got a max of 0, they didn't tell me anything about the sign of f, the SIGN sign. So I can stick these mins and maxes wherever I want. Okay? They didn't tell me anything about the sign of f. So I'm going to put a max, I'll just stick it right here. Okay? Now I know if this is a max, peeps, it's going to look like that, right? And then I got mins at 2 and negative 2. Okay, so I'll put them in right here. And maybe right here. And I know that we're going to be like this. So I'm thinking this, right? Those are mins. Now, it turns out, because I thought that, this right here is going to fall into my lap. Because I drew this the way it went, these two things are going to fall into my lap. This is telling me the second derivative is negative. We got concave down, right? So we're concave down between negative 1 and 1. So here's negative 1, here's positive 1. So we're concave down. Boom. Okay? Then we're concave up between negative 3 and 1. So concave up. Boom. So I'm going to put a dot there. That's going to be the indicate where that's where the concavity switch. What do we call that? The inflection point. AJ, that's the one that you wanted to, that you meant a minute ago. Okay? And then concave up from 1 to 3. So, ooh, this one I missed. Okay? I can stop it there. And so I'll put a dot there to indicate that's where the concavity changes. Now, I'll be honest, I missed that a little bit. Okay? The inflection point, the way I have my graph, the inflection point is really more like right there. And probably more like right there. It's not quite at 1. But we get the idea. Okay? Happy with that? So here's my question for you. They didn't tell us anything about the sign of f. So I could have stuck this, made these maxes super tall, made these mins super low, put this anywhere I want. But this is been the graph. Could I have drawn this as the answer?
No,
Whoa! Jimmy,
because there's no concavity at all there.
how do you know that?
Because I was just thinking about it.
Like,
Okay? Enlighten us what you were thinking
the
about.
rate of change isn't changing.
The rate of change isn't changing. Why do you know that?
Because it's a straight line.
These are constant slopes. Constant slope, constant slope, constant slope, right? The rate of change isn't changing. In fact, the second derivative for this graph right here, the second derivative would be what? Everywhere. Except here, here, and here, because the first derivative doesn't exist. Zero. Okay? So this wouldn't work here. You had to have some curving. All right? All right. Good stuff. Good stuff. You want to do one of the other ones? The ones that the other classes have asked about have been, I don't know, my book's way over there. I think it's 221.
Oh yeah, 221.
Yeah, 221 and 222, okay? So if you think about 221 and 222, 221 and 222 give you a function, and they say, okay, here's our function. This is 221. F of x is sine of x plus sine cubed of x. And then they give us this interval, negative pi to pi. Actually, they give me this open interval. Right? And they say, find the local max and the local min, find where the function's increasing, and find where the function's decreasing. Okay? AKA, find where the first derivative changes sign from positive to negative or negative to positive, and find where the first derivative is positive and where the first derivative is negative. That's what's telling you all that information. What's the first derivative doing? Okay? Now, in all honesty, you could have done this problem last year in Chris' class or Snyder's class. You didn't need calculus to do this problem because you had Desmos. You had a graphing calculator. You could have stuck that in the calculator, hit graph, then answered all these questions. You could have found the max on the calculator. Heck, they do that in Algebra 1 now. Okay? Well, no, we very much do. This problem, I would argue this problem is kind of antiquated. You know that word? Antiquated? It means kind of, I wrote it out, it looks like antique. It's kind of an antique problem, right? I mean, it's out of date. Like, back when I was in calculus, we had to do tons of problems like this. They'd give us a function, we'd have to analyze the crap out of that thing. Take the first derivative, set it equals 0, find positives and negatives, take the second derivative, find where the function's concave out, where it's concave down. Then we'd have to tie all that stuff together and sketch a graph. Okay? In some ways, I would argue that's kind of antiquated. Like, that's why I focus more on, like, okay, let's analyze these graphs. Tell me what the derivative is doing. Kids would get bogged down in that sketching of the graph thing. Like, just silly. Talk to me why do you know that function's increasing? Oh, the derivative is positive. Oh, okay. But we're not gonna sketch this, but we can at least do this little analysis. And there's some fun algebra here because we got to review our trig. So in order to analyze the derivative, we pretty much have to do what first here? Find it. I feel like I'm talking to my dog. Find it. Okay. What's the derivative of sine of x? Cosine of x. What's the derivative of sine cubed of x? 3 sine squared of x times cosine of x. You should be able to do that derivative that quickly. That should be an exercise to you. That should not be a like, oh God, how do I do this? That should be a no-brainer to you. Okay? Hopefully it is. What are we going to do now? Set it equal to 0? Woo. Cosine of x plus 3 sine squared of x cosine of x. Oh man, how do I put on my trig algebra pants here? What are we gonna do? Factor out a cosine? Like that? How do you like that? You good? Okay. No? Who said no? Emmy? Was that you that said no? Oh, this is- All right, so what do we do now? Do we know how to do this algebra? Are you with me?
Yeah.
Emmy, are you with me? Emmy? So we do that. Then we do this. And honestly, guys, this is about as hard as the algebra is going to get for me when it comes to this stuff. Okay? So, where's the cosine 0? One.
Pi over 2. Pi over 2?
Pi over 2. The pi over 2 family. Cosine is 0, right? Now I gotta hold on. And when we did this yesterday, you guys can hear me because I didn't see the back. When we did this yesterday, this is the only one I listed when we first did it. I forgot about one, but I don't want people online to hear it, but I did that. There's another one between negative pi and pi. It's a sneaky one.
Negative pi over 2?
Negative pi over 2. When I did it yesterday, I was like, oh, cosine 0 at pi over 2 and 3 pi over 2. Oh, 3 pi over 2, that's outside of this, so we don't care. All right. Dang it, forgot that coterminal angle. So, I got this other one here, negative pi over 2. All right, let's go over here. We got that one done. So we got 3 sine squared equals negative 1. Sine squared is negative 1/3. What's the solution to that? Guess what? There is a solution. Why? Nothing squared is going to equal negative 1/3. Man, whoo! Thank God we didn't have to do any crazy stuff with the unit circle. Okay? There's no solution there. But I got 2 solutions here. Okay, so we're going to make a quick sign chart. Let's do that up here. Okay, of course, when you make a sign chart, you should label him. Okay, give him a, tell us who he is. Okay, and I'm going to put negative pi over 2 here and pi over 2 here. And then I'm going to put a little cap there. What are these little caps representing? Pi and negative pi, right? Technically speaking, guys, this function is periodic. That's why they capped it off here for us. Okay? Okay, so if I'm looking at this, okay, here's the derivative. And when we're doing this testing of the derivative, it's really nice if you look at it when you have it in factored form, because you can do some quick math. All right? If I'm looking at this right here, this derivative, 1 plus 3 sine squared, that no matter what x is always positive. Right? No matter what x is, this part is always positive. So the thing that's going to drive the sign of the derivative is this. Right? So now, if I go over here, and I look at a value of x between negative pi over 2 and negative pi, is the cosine going to be positive or negative? You actually don't even need to test a value, because you know that between negative pi over 2 and pi, here's negative pi over 2, here's negative pi. Okay? So between negative pi over 2 and pi, what quadrant is that? It's in the third. You know that the cosine is always negative. And since that's the thing driving the sign of the derivative, we don't even have to actually plug in a value and test it. If you wanted to plug in values, take a number in there, knock yourself out. Okay? What about between negative pi over 2 and pi over 2? What quadrant is that? Or quadrants?
4 and 1 is going to be positive.
1 and 4, and it's going to be positive. And what about between pi over 2 and pi? Negative. Negative again, right? So now, here we go. Here, ready? This sign chart gives us all the information that we need. All we have to do now is just, we don't have to graph it. We don't even have to graph this function. We just have to put the information that's in this sign chart and put it into words. So this is telling me f is increasing. Where? Where's the first derivative positive? Okay? I like interval notation better than inequalities. It's kind of easier to read. The book likes the inequalities. They're dumb. F.
Hold on.
Huh?
Why is it so why is it increasing if it goes from positive to negative again from pi over 2 to pi over 2? It's positive, but
What's positive?
from negative pi over 2 to pi over 2 is positive.
Who's it?
The
Nah.
the derivative.
The derivative is positive. If the derivative
we're
is,
looking at f. Okay.
yeah, f is
Okay.
increasing.
Okay.
Okay? I don't know about f prime's increasing or decreasing behavior.
Okay.
What's going to tell me about that? F double prime. They didn't ask me to find that. Thank God, because I don't want to find the derivative of this. Yeah, it's going to be a product rule in there. Yeah, it's going to be nasty. Okay? F is decreasing. Where is f decreasing, AJ?
From negative pi to negative pi over 2 and pi over 2.
You guys okay with that little U?
Yeah.
Seen that before? Now, we got also a piece of information here. We have f has a local max at where? Where does the f have a local max? Where's the first derivative change from positive to negative? Or better yet, where do you switch from increasing to decreasing? Pi over 2. And f has local mins at x equals negative pi over 2, and that's it. Oh, we only have one min. Okay? So we answered the question that they asked us. They didn't ask us to sketch a graph. In all honesty, in order to sketch that graph, we would have had to have probably looked at the second derivative to do it justice. And we can get a general idea, but we're not going to get as good of an idea with shape unless we look at the second derivative. Because that's going to tell us the concavity. Okay, so I have to ask you this. We're going to go down this little rabbit hole. So this is period 4-5 we get out of 09. Okay, so which is in 10 minutes. We're going to go down this rabbit hole for a second. Okay? And Samuel noticed this when he walked in, and he wanted to already fight about it.
We had this conversation last year.
Can I do that?
No, you can't.
You say no? Why?
Because it can't be both increasing and decreasing at the same time.
Why?
So because if it's increasing, then it's not decreasing. It'd be in the middle,
What's it mean to be increasing?
going up.
Going up? Samuel, what do you think?
I think that that it can't be true because like I said, it can't be increasing and decreasing at the same time. Because if what increasing is if x approaches infinity, y approaches infinity, or so, or x increases, y increases.
Okay, that's better. You don't have to necessarily go to infinity.
Right,
Yeah.
And then when it's decreasing, as x increases, y decreases. And they can't both be true. So that would mean it's increasing and decreasing. I think it's split function.
Well, okay, let me ask you this. What both of you guys have said, you're introducing some sort of comparison. You're defining increasing to be going up in y values. As x increases, y increases. So, if you've got this x value right here, you f it. You got this x value right here, you f it. This one's bigger than this one. Right? And then you got another x value, you got this x value, you have this one, this one's bigger than this one. That's what you're telling me increasing is. And you're increasing if you can do that for all the x values. Right? And decreasing, same thing. This x value here, f it. This value, x value right here, which is bigger, f that, he's smaller. Go to another one. You can do this any two x values that you pick. You should be able to f them both, and the second one's going to be smaller than the first. Or f them both, and the second one's going to be bigger than the first one, if you're interested. So if that's true, then why does that not work? Is it true that I can take any two x values in here and f them both, and the second one's going to be bigger than the first one? Even if I chose the very, very, very end? If I choose this one as my first one, and I f the next one, was it increasing that time? Yeah. And if I choose this one as my second one, was it decreasing that whole time? Yeah. If we define increasing and decreasing that way, that's how you have to write it. But it wasn't until you guys learned some calculus where all of a sudden this idea of slope and rate of change came in. And then all of a sudden it was like, oh, you're increasing when the derivative is positive. Right? Well, the derivative is not positive at pi over 2 and negative pi over 2. What's the derivative there? It's 0. Okay? Either way you write it, it's accepted. But if you define increasing and decreasing like the way it's traditionally introduced, then that is actually the correct way of writing it. You can be increasing and decreasing at pi over 2. Because really there's no such thing as increasing or decreasing at a point. You're like, oh, you can't be increasing and decreasing at the same time. You're right, you can't be increasing or decreasing at any time. It has to be over an interval. Okay? It's like if you're riding the beach at Kings Island. You're going up the hill. When do you start going down? Like, you don't start going down until after you roll over the top. You would have said I was going up until I got to,
Isn't there some paradox about that?
Yeah.
You can't be moving at any given instant, so it makes sense that.
I mean, technically speaking, you're at that instant you're not going up or down, but it is what it is. I've sat in rooms with math teachers before. Like earlier in my career, I would go to these workshops and math teachers would argue about this. Like, you got to put the endpoints. Like they would. Most calculus teachers who weren't as like pure mathematicians would have argued for the open parentheses. Most calculus teachers who were more like interested in the pure math side argued that. But either was accepted. If you were taking the AP test, they would. So let's do this. We didn't get to do this last period because I was screwing around with that live stream thing, but now we know it works. Emmy's out there. She's probably the only one watching. This is going to blow up YouTube.
So with the live stream, are you still doing the same lessons in class or two different lessons?
So starting next week, if this live stream thing is, if I feel like this worked, starting next week, what we do on Monday, you'll want to watch on Monday. And what we do on Tuesday, they'll want to watch on Tuesday. That's my hope. Now, and we'll only have to do that next week. If we end up on the same hybrid schedule for some reason, then we'll continue that on. If we end up back everybody here, then the only people that would need to watch this would be the people who are at home sick or who have chosen online only. Does that make sense? I'm trying to make this easiest so I'm not like doing 3 different things. And if I end up having to do 3 different things, I mean, I will, but right now the big issue that I'm facing here is right now Emmy can see me really well in this board right here, but she has no idea about the Rachel story, like that I drew over there. Like, what was he talking about? The sidewalk? Or if I stuck a graph up there on Desmond, she wouldn't have seen that. Unless Jimmy would have been the camera guy and rotated the camera, But I don't know if I want one of you guys responsible for running video equipment, So, but I think I might have gotten this thing working again. So I might move the camera over here, and then I'm going to start writing on the smartboard. But my projector just stinks. Yeah.
You actually do ever do the settings on that? I know a lot of how to do it.
I have no idea what you're saying.
I was saying, if you ever need help, setting up a live stream stuff, I know a lot.
Oh, well, I was able to set it up. It's what happened last period. I ran a test during first period. I had it set up. I created a new live stream, ready to hit play, or go live for third period. When class started, I hit go live. Camera wasn't recognized, and I did. So here's the thing. For whatever reason, we were able to accomplish much more yesterday. I don't know why, but it is what it is. Who cares? So on Monday, I do want you guys to try to tune into that live stream on Monday. I will revisit everything that we did with that group of kids. I'll redo that on Monday. So, yeah.
Could you run something on Google talking about that and I forget?
Yeah, I'll do that in a second.
See you Tuesday.
See ya. Bye, Emmy. I hope you feel better.
This is the team right 15, having increasing in.
Yeah, I know. I used to think that way. I was like, no way. And then as I started looking more at the math of it,
Can you unpause the thing? The retake.
oh, yeah.
Have a good weekend.
See ya.
That's too much, but I appreciate it.